Hello, friends. Good day to all of you. Today, now I'm here with a new video, which is actually in continuation with the earlier videos which I have posted on the lubrication system or the lube oil properties and all these things. So, this is one of the very basic concept regarding the type of lubrication system also, because we have main engine, we have generator engines, other auxiliary machinery, compressor, purifier. So different places you have lubrication, different types. So in this video, we are going to basically see the various types of lubrication system on ship. You can see here the types of lubrication. Basically, there are four types of lubrication system. Number one, boundary lubrication system, hydrostatic lubrication system, hydrodynamic lubrication, elastohydrodynamic lubrication. So these are the four major. Other types also there, but these are the four major we are going to see in cover in this video. Hydrostatic lubrication. Okay. So what basically is the hydrostatic lubrication? It is a system where the external high pressure pump forces the lubricating oil between the two rubbing surfaces, basically to create a thick fluid film and completely separating these surfaces before any movement occurs. So we are starting the lube oil pumps, especially if we talk about the main engine. So what happens? The pressure is generated, and this pressure, the lube oil is going to pass through the rubbing surfaces, bearings, or con rod part. You can see all over where the lube oil is passing through. So this is something which is going to create a separation between the two rubbing surfaces due to the high pressure which is being provided by the pump. And this type of lubrication is called hydrostatic lubrication. But what happened in hydrodynamic lubrication? Basically, it relies on the high speed rotation of the shaft. What happened? The shaft started rotating and draw the oil and form the wedge. And due to the wedge formation, it generates own pressure and separate the rubbing surfaces. But hydrostatic system does not require any relative motion. This is the most important point. It does not require any relative motion between the parts to create the lift. Lift means the two rubbing surfaces, two journals, bearings, and all these things, you can say that. So it is going to create the separation due to the pump pressure. How the hydrostatic lubrication works, as we have seen, compressor. So first the pressurization part is coming into picture. Before the machinery begins to move, there is no movement now, begins to move, an external pump delivers oil at high pressure into the recess pockets within the bearing. So the pump is pressurizing the oil into the recesses. Then after that, what will happen in the second phase? Lifting the load. So load is being taken by the oil. The pressure build up in these pockets until it overcomes the downward force, that is your weight, of the heavy machineries, the components such as shaft or the crosshead pin. So what happens? Basically, there will be a separation and it is taking the whole load of the machineries. Third, fluid film separation. The component is literally lifted and floats on the continuous film of the lube oil and preventing any metal to metal contact even at zero speed. So the most important thing, at zero speed also, there already the separation is being created. And due to this, we have the word called hydrostatic lubrication. Okay. Here you can see this is the pump which is taking suction the lube oil, and allowing the supply. And here you can see the journal bearing system. So it is at rest. First condition is at rest. So what happened? The contact is already there. You can see the weight of the journal is on this, and there is a contact in this. Okay. So what happened after, once the oil is completely, the oil is slowly started filling up. The oil is completely slowly filling up. And once the oil is completely filled up, you can see the journal is already lifted. The weight is being taken by the lube oil. The lube oil which is here, it takes the weight, and the separation already is started. So journal, when it comes at full speed, then this is something which is there. So this is the separation already started, and then we are going to start the machinery. Then no problem, because already we have the load is being taken care of by the lube oil. There is no direct contact, as you can see in this part. So this is something which is going to tell you about the complete hydrostatic part of it. Key application on ship equipments. Okay, so what are the key applications? Basically, we can see over here, the hydrostatic lubrication is critical for heavy components that either move too slowly to generate their own oil wedge or to experience massive load during startup. So two major points are there when we talk about the ship's equipment. One is the speed of rotation, if the speed is less, or another is the massive loads at the time of startup. So these two things are very important we have to see. So crosshead bearings in two-stroke engines. Crosshead pin only oscillates, swing back and forth. So the movement is back and forth, rather than completing a full rotation, and moves relatively slow under the extreme firing loads. So the combustion is there. You can see how much pressure is on top of the piston. We know that peak pressure and all. So the separation is required. It cannot generate an adequate hydrodynamic oil wedge in case of the hydrodynamic lubrication. So what happened? Marine engines use a dedicated crosshead lubrication pump generally, and often boosting pressure 10 to 12 bar or higher to provide the hydrostatic lift and ensuring the bearing does not wipe under the immense pressure of the pumps. So this is one of the example, but I am not completely with this dedicated crosshead lubricating pump. Earlier it was there. I have seen also in soldier engines and all. I have seen this part, but now we have, like in BMW and all, there is no dedicated crosshead pump. The same oil is going, and they are generating. So actually, the lubrication in case of soldier, lubrication in case of the BMW and all, that will be discussed in another video. But just to remember this, the hydrostatic lubrication occurs over there. Okay. Okay. Now we will see another example for this is your main engine startup. When the main engine is going to start, how it happens, what are the things happens? Hydrostatic jacking. For every large main engine, crankshaft or the propeller shaft resting heavily on their journal bearings. So basically, we in our ships, what happened? The crankshaft is connected with the intermediate shaft, and intermediate shaft is connected with the propeller shaft, and then the propeller comes into. But the all load basically is resting on the journal bearing part of it, starting from 0 RPM, because at the start the RPM is 0. And if there is nothing, then it can cause the severe boundary lubrication, metal scrapping to metal, metal contact to metal contact. But what we are doing, we are starting the lube oil pump. And once we start the lube oil pump, the pressurized oil goes into it and it creates the separation. So hydrostatic system basically used to jack up or lift up the shaft due to the oil film between the shaft and the bearing. And what we do, we turn the engine with the help of turning gear. And after that, we just blow through the engines and all. So that is a different part. But all these things helps basically to maintain the sufficient separation between metal to metal contact. Thrust plugs, heavy duty thrust plugs. So while marine thrust bearing, missile tilted pad bearing type. So thrust primarily use the hydrodynamic lubrication at sea because the speed is there. Some incorporating hydrostatic oil injection to separate the pads and thrust collar during the slow speed maneuvering or the startup time. At the startup time or at the slow speed, dead slow ahead, dead slow astern, and slow ahead and all. So these things are there. So anyway, thrust block lubrication and all, it's a separate topic. So we will discuss it afterwards. Okay, why ships use it? Why we are utilizing this one? What is the benefit? What are the advantage? Zero speed protection. So when we talk about this zero speed protection, we can see this one. Just a minute. Zero speed protection. It eliminates wear, dry running, and high friction when the engine is starting, stopping, or with the turning gear. So we can easily run the engine, turn the engine, and all because we know that there is a separation already exists because the lube oil pump already started earlier. That's why we are saying lube oil, start the lube oil pump, start the lubrication well before starting the engine, at least 1 hour or 2 hour basis. So there is no chance of having any contact. The separation is sufficient. High load capacity. The load carrying ability depends entirely on the external pump's pressure, not the rotational speed of the engine. So we have the separate lube oil pump. We are starting that, and the load already being taken by the lube oil. Low starting friction because we have already the separation. So starting friction, low starting friction, no friction because the surface are fully separated by the fluid before any movement starts. So already the separation exists. So starting torque required to turn a massive marine engine drastically reduced. So the large torque which is required to turn the engine is not there because we all the journals are floating. That's why with a small turning gear motor, we will be able to turn the engine easily. There is no problem in that. So because there is no direct contact, it's already separated. Okay, now we will go for the another concept, hydrodynamic lubrication. We have just seen the hydrostatic part. Now we will go for the hydrodynamic lubrication. This is the most useful one. Okay. So hydrodynamic lubrication is a self-generating fluid film lubrication. And it happens due to the relative motion between the moving surfaces. This is the most important. Hydrostatic in the static. There is no motion at rest. But when we talk about hydrodynamic, we have a relative motion between the moving surfaces. It draws oil into the narrow gap and creates a converging wedge. I will show you the diagram also. Don't worry. So I have that part also. And it generates the internal fluid pressure high enough to completely separate the surfaces without needing any external high pressure pump. So once the motion started, once the relative motion started, then this is sufficient enough to generate the self lubricating film and the separation will happen. And in hydrostatic lubrication, which is wholly depending on the external pump pressure at zero speed. And hydrodynamic lubrication is having the speed of rotation and of course the viscosity of the oil. So oil quality also matters. We will see this. Here you can see the hydrodynamic lubrication. You have the bearing part and you have the shaft or the journal part. And the lube oil is over here. The load is directly on this bottom. And this is something which is at the rest. But when it starts with the motion, it creates the lube oil film and there will be a separation. I will show you that also. This is the starting condition part. And here you can see this is your shaft, this is your bearing part, and the separation is there. So the lube oil already floats in between this part of it. Okay. Here you can see the starting part. We have this is the static part. So here the shaft and the bearing and the load is directly on down. So once the motion starts, so as the motion starts, the starting of part, then there will be the starting creation of the wedge formation. And now it is with the full motion part. So you can see that the converging, diverging wedge creation. So you can see that this is the pressure distribution diagram. You can see when it is running with the shaft is running with the full speed. You can see the load is being taken up by, and this loop oil is carrying the load, and sufficient separation is also there. Okay, I will show you with another diagram. Here you can see the high pressure area, shaft at rest, and loop oil is also there. So once you have high pressure area, shaft is starting to rotate, just starting. So it squeezes the oil, and some of the oil goes over here also due to the motion of the shaft. And then there will be another oil. So high pressure area, shaft at full speed. So their load will be carried out by the lube oil, and always there will be a lube oil due to the motion of the shaft. It's act like a pump, and it does not require any external pump. And this lube oil is having all around with the shaft as the shaft rotates. Here you can see this is the curve, the speed in meter per second in the x-axis, and friction coefficient mu in the y-axis. So this you can see they're starting with the boundary lubrication part. Here you can the strike back curve. So up till this minimum speed. So up till this you have the boundary lubrication. Some part you can see, some of the part may have the contact. Otherwise lube oil is also there. Separation is also there. So we will see the boundary lubrication concept also. And this is something which is your mixed. Here the boundary and hydrodynamic mix, because the shaft started, the speed started increasing in the x-axis. So the speed of the shaft is increasing. So slowly you can see the friction coefficient started decreasing. So earlier it was almost the same, and after that the decreasing start at the motion increase, it decreases, and after certain speed it started, the friction coefficient also started increasing, and after that it is going to maintain at very high speed at certain limit. Okay, and there you can see the sufficient separation between the two surfaces, your journal as well as the bearing already exists. So it is not going to be, it is going to be stabilizes at some point. So this is the process. Start with the boundary, then go for mixed, and then it's going for hydrodynamic. We will see that part later, the boundary lubrication. Here how the shaft is going to rotate, the lube oil is already existing, and once the motion will happen, this is the bearing part, and it is going to take up the oil, and then it is going to move completely like this, and this creates the wedge formation, and it creates the separation between the shaft and the bearing part of it. You can see this is the pressure distribution part of it. Okay. Here again the oil pressure distribution across the converging wedge of the journal bearing. You can see the lift force. This creates the lift. Okay, so basically the force is acting, and this is the bearing part. This is your shaft or the journal part. And once the motion, this is your motion starts like this, and you can see that the oil squeezes between these surfaces, and this is your diverging wedge. You can see it is written diverging wedge. So this is diverging wedge of the lube oil, and after that, and this part is also cavitation. Sometimes what happened, the lube oil is not present over here, and then this is going to go through this side. Now this is your converging wedge. So it is going to create the separation of the shaft and the bearing part of it. And here, from here, you can see the load distribution starts. You can see this much separation, this much of the pressure, oil distribution pressure, and this basically the pressure you can see creates the lift force. And due to the lift force, the shaft will be separated from the bearing, and this is something which, and this distance is called MOFT. We will see this part also. Okay, so this is something which is a clear understanding and explanation of the hydrodynamic lubrication, wedge formation, the diverging wedge, and the converging wedge of this case. Okay. So the three required conditions for the hydrodynamic lubrication. One is your relative motion, another one is your converging geometry, and your viscous lubricant. Yes, lubricant quality is also very important. if it is not sufficiently viscous, or you can say the property of the lubricant is not such that so it can the carry load. If it is not thick type, if it is a thin type, then the separation cannot exist and the contact will happen. Okay. Aerodynamic lubrication to form and maintain itself in a ship machinery, three conditions: relative motion. The shaft or the collar must rotate at sufficient speed to drag the lubricant into the contact zone via viscous adhesion. So we have to have the sufficient movement, the shaft and bearing in between that. Otherwise, the pumping action will not start. The converging and diverging wedge will not be developed, and the separation or the lift will not be developed between the journal and the shaft. Converging geometry. The clearance spaces between the surfaces must narrow in the direction of motion and creates a wedge shape formation of the lube oil. So wedge formation will start, which I have already explained in the previous diagram. Viscous lubricant. The oil must have the adequate dynamic viscosity to maintain the film thickness under the applied load. This is the most important part, selection of the oil. So that's why you will see on board ship we have the lube oil charts for the various machineries. And accordingly, not only this load carrying part, not only the other thing, as per the other lubrication requirement also. And the chart basically given the complete idea regarding the which machinery require which type of lubricant. If it is a hydraulic oil, if it is used for the main engine system oil or the generator sump oil, cylinder lubrication part, purifier, compressor. So different oils have the different qualities. So this viscosity, dynamic viscosity of oil is sufficient enough to maintain the film thickness and carry the load, create the separation. Okay. So how the dynamic wedge is started or develops. So at rest, at zero speed, what happened? The shaft rests directly on the bottom side due to the gravity and creating the boundary lubrication, metal to metal contact. So I have shown you this in the starting part of it. Next, startup, low speed. As rotation begins, the shaft attempts to climb the bearing wall in the direction opposite to the rotation due to the surface friction. So basically, shaft is attempting that part. Then next is your normal operating speed. So there must be sufficient speed. The viscous drag basically pulls the oil into the narrowing clearance space between the journal and the bearing and the downward side. Oil cannot escape fast enough, that causes the internal pressure to surge. So basically the rotation is already started of the shaft and oil cannot escape. So what will happen? The pressure will start developing, and this pressure creates the upward lift. You can see P is equal to mu u by h square. So this is going to create a minimum oil fill thickness that I have shown you in the diagram. The separation between the journal and bearing, that is called minimum oil fill thickness, MOFT. Sometimes in the orals also this is being asked in case of hydrodynamic lubrication. Okay, what is MOFT? Pushing the shaft into the eccentric floating position with continuous minimum oil film thickness. And this is possible only due to the upward lift created by the hydrodynamic wedge. So this you have to understand. So I am not going much deep into the explanation of this formula and all, but I am just showing you that the pressure which is generated, it is directly proportional to the coefficient of friction, speed, and the x. Okay. So this is going to create a MOFT, that is your minimum oil film thickness. Okay, so that's how the hydrodynamic wedge creation happens. The pressure generates, the lift happen, and this creates the separation between the journal and bearing. Okay, what are the marine applications? Main engine, crankshaft, bottom end bearings. Once they reach the sufficient RPM, high rotational speed, it generates the hydrodynamic film across the bearings. Okay. And missile and Kingsbury thrust block also, here also it is happening. Main propulsion thrust bearing, use the pivot tilting pads, and thrust collar rotates with the propeller shaft, and each pad basically automatically tilts at some angle to form the self-adjusting hydrodynamic oil wedge, and it absorbs the thousands of kilonewtons of the axial propeller thrust. So this thrust block lubrication is a separate topic basically. And I'm planning to do that. I'm going to make the clear understanding and explanation of the thrust block lubrication also. So basically, the thrust bearing have the tilting pads, and they tilt in such a way that the separation between the uh, contact surface happen, and the lube oil comes in between, and the sufficient thrust and pressure which is being generated by the propeller shaft is being absorbed by that. So this is something which is a very interesting topic. So I will discuss it later on. Primary marine applications. Another thing is your stern tube and intermediate shaft bearing. So in how this is basically happening, the stern tube part of it. The propeller shaft floats on the aerodynamic film inside the stern tube bearing, oil lubricated white metal bearing, or even the water lubricated bearing. So the stern tube lubrication is also coming under the your aerodynamic part, because the propeller shaft turns and it does the same thing that journal and bearing separation. Okay. Turbines and turbochargers, auxiliary turbines, high rotational speed, 10,000 to 20,000 RPM. Generator turbochargers are high speed. Main engine is even less, but that is also in between the range of this 10,000 to 20,000, maybe 12,000, 13,000 RPM at high speed. So this also creates the hydrodynamic wedge and the separation between the journal and the bearing. So turbines and turbochargers also have the hydrodynamic lubrication. Here you can see the glance at a glance how we have the first column gives you some of the features or the things, and hydrodynamic lubrication and hydrostatic lubrication. Okay. And you can say as a difference part also. Pressure source requirement, self-generated by the shaft rotating in the wedge. So in case of hydrodynamic lubrication, it is self-generated. But in case of hydrostatic, external pump is required to force the oil between the pumps. Motion required. Yes, hydrodynamic lubrication is basically the concept of relative motion. Otherwise, the at zero speed there is no hydrodynamic lubrication. But it is not like that. Hydrostatic lubrication does not require any motion. External pump will pressurize the oil and separates the journal and in a standstill condition also the hydrostatic lubrication happens. Starting friction, high at the initial, instant, boundary contact. Some of the spaces have the contacts. Very low in the starting. Why? Because shaft already lifted before the rotation happens. And the core marine uses, running main bearing, thrust pads, and turbos. Crosshead pins, startup shaft, and then the jacking or lifting of the shaft. So these are some of the differences, just as a overview part of it. Okay. Boundary lubrication. What is this? We have already seen the hydrostatic, hydrodynamic. Now it is very easy to understand for you guys the boundary lubrication part of it. Boundary lubrication occurs when the fluid film between two sliding surfaces becomes so thin that microscopic peaks on the metal surfaces comes in direct physical contact. Here the lube oil is there, separation is there, but in that one, the some of the metal to metal contact happened, and these are the microscope. Unlike the hydrodynamic or hydrostatic lubrication, where the lube oil film completely floats between the moving parts, in case of hydrodynamic and the hydrostatic, due to the oil pressure, it is separated. Boundary lubrication relies on the chemical surface film moved by the oil additives. Boundary lubrication basically relies on the chemical surface film forms by the oil additives rather than the fluid dynamic pressure to prevent the severe friction, wear, and scuffle. So it is something which is a different concept altogether. So the lubrication happens, the separation happens, but some of the macroscopic peaks are in contact. Now it is easily understandable by you guys. First is your boundary lubrication. Mixed lubrication I have shown you in the graph also, and hydrodynamic lubrication. The applied force you can see is F, and the motion is like this. So you can see in boundary lubrication, lube oil is there. The peak, this separation is there, but somewhere you have the microscopic contact like this, and you can see over there. So these are the microscopic contacts in case of the boundary lubrication. The motion starts, and the mixed lubrication you can see complete separation. So it is a boundary and hydrodynamic mix. The process goes on, and once the complete speed, the rotational speed is already gained, you have the sufficient, and this age is MOF2. Okay. So this is something which is a complete separation. Now already the establishment of hydrodynamic lubrication occurs. Where the boundary lubrication occur on board ship? Boundary lubrication is usually an unavoidable transitional stage. Or you can see the top dead center, TDC of the main engine cylinder liners. There. Near TDC, the top piston ring slows down and comes to a momentarily stop, transitional period, and reverse the direction. Because of the sliding speed becomes to zero, aerodynamic wedge generation is collapsed. And then this boundary lubrication starts. Combined with a maximum combustion gas pressure pushing on the top ring outward against the liner and intense local heat lowering the oil viscosity, boundary lubrication contact occurs at every stroke. So this is a very nice explanation. Basically, you have the high gas pressure on top of the piston, and not only that, we talk about the lube oil condition, the oil viscosity, the viscosity will also drop because of the high temperature. So how to maintain the sufficient oil film thickness? So that's why the boundary lubrication exists over there. This is very important to understand. This is a transitional phase. Okay. Start up and stop before the heavy crankshaft or the line shaft reaches the sufficient rotational speed. We have seen in the diagram also boundary lubrication, then go for the mixed lubrication, and then the hydrodynamic lubrication starts. So hydrodynamic wedge, once it will be formed, then the hydrodynamic lubrication will be there. It's a transitional phase. Reduction gear teeth contacts. Yes, the teeth contacts between the gears. High contact stress and combined rolling and sliding motion at gear tooth tips and the roots squeezes out the bulk oil film and forcing the reliance on boundary film protection. So there also you will have. So once you inspect the any gear, either you talk about the pump also, gear pump also, you will see the contacts between the gear teeth. So this is the indication that boundary lubrication is there, and some of the microscopic contacts established during the lubrication part of it. Mooring winches, deck cranes, steering gear pins. So all this has to be oscillating movement, slow speed movement. So there you will see the boundary lubrication. Wire ropes operate almost permanently in the boundary lubrication regime. So these are the part of. Here you can see the boundary lubrication part. So boundary lubrication at dead centers. The fluid fill, the cylinder oil, which you can see, the top force, the combustive force, the peak pressure on top of the piston. And not only that, the harsh condition is the temperature also. You will have the high temperature inside the engine cylinder. So this also reduces the viscosity of the fill. Okay. So top dead center, TDC, bottom dead center, BDC. There is a reversal of motion. So momentarily, it is having the stop condition and then change the direction of rotation at both dead centers. So you will have the boundary lubrication on top of this. Okay, now we are going to see about the all three lubrications. That is your hydrostatic lubrication, hydrodynamic lubrication, and the boundary lubrication. So we are going to compare these three. Okay. So first column is parameters, and rest all three is your hydrostatic, hydrodynamic, and boundary lubrication. So first parameter is your film thickness, H. So lubricating oil film thickness. If you talk about the hydrostatic lubrication, the film thickness is thick. H is greater than 10 micrometer. If we talk about the hydrodynamic, then it is moderate. H is between 5 to 20 micrometer. And when we talk about the boundary, molecular surface, boundary lubrication, very molecular surface, H is less than 1 micrometer. So this is the part. So when we talk about this 10 micrometer, it is more, quite more. And in this hydrodynamic, it is varying. Why? Because depending upon the relative motion. So that's why it is saying 5 to 20. So it can be less also. When the speed increases, then depends upon that, the thickness also changes. So all these things are there in the moderate part. Okay. Surface contact. In hydrostatic, zero surface contact. Because as we have the high pressure oil comes and the journal lifts in the bearing. In hydrodynamic also, once the hydrodynamic lubrication exists, then zero contact. But when we talk about boundary, we have direct contact, but it is a microscopic contact, some of the points. We have seen in the diagram also. What about the pressure source? In hydrostatic lubrication, the external high pressure pump is required to create the pressure and create the lift. When we talk about hydrodynamic, it's a self-generated wedge creation, and it depends basically on the speed and the rotation of the shaft. And boundary lubrication, these are high pressure additives, chemical additives are there in the lube. So the reaction happens on that. What about the friction coefficient, mu? Very low in case of the hydrostatic because there is no contact or not. 0.001 to 0.005. Here in hydrodynamic also 0.00 very low, 0.001 to 0, but in case of boundary, yes, it is high, 0.05 to 0.15, where depending upon the boundary lubrication. Primary marine examples where these things are being utilized. Crosshead pin, lift, pump shaft jacking. So all this hydrostatic is basically at the starting part also. Hydrodynamic, running main journal and thrust bearings, hydrodynamic lubrication, main bearings, journal bearings, thrust bearings. BDC part, where basically the reversal of direction of the piston movement happen. So this is the best example of the boundary. Okay. So then next, we are going to discuss about the elasto-hydrodynamic lubrication. Elasto-hydrodynamic lubrication. This is defined as the condition where the lubrication occur between the point contact and line contact of the moving surface. So this lubrication is based on the point contact and the line contact of the surface. In case of point and line contacts, hydrodynamic fluid, that lubrication is not fully established. So why we are talking about the point contact and the line contact? Because the hydrodynamic lubrication does not established fully, and elasto-hydrodynamic lubrication exists at that point due to the elastic deformation of metallic surfaces. So please note down this one, that elastic deformation of the metallic surface happened, and that's why this is called the elasto-hydrodynamic lubrication. This is also known as the squeeze film lubrication. What is the example? Lubrication between the rolling surfaces and a roller bearing. So this is something which is your squeeze film lubrication or elasto-hydrodynamic lubrication. Elasto-hydrodynamic lubrication is a specialized form of hydrodynamic lubrication that occurs in non-conforming contacts, where two curved surface meet at the tiny line or the point. So as we have seen in the rolling surface also, these are the roller bearings. So they have the curved surfaces and they meet at the line. Okay. So either line contact is there or either point contact is there. So gear teeth of the rolling element bearings and all. So they are this type of elasto-hydrodynamic lubrication occur. Okay. And squeeze film lubrication also. The extremely high localized contact pressure is very high, 0.5 to 3 GPa, gigapascal. So here we have at point contact or at line contact, we have a very high pressure. We will see this. the core physical mechanism behind this elastohydrodynamic lubrication. When two hard and curved metal surfaces, so metal surfaces has to be curved, are pressed together under the heavy load, standard hydrodynamic theory predicts that the oil will simply be squeezed out. So due to the high pressure and the line contact and this, the oil will squeezed out, leading to the several metal contacts. Not several, sorry, severe metal contacts. So in this one, how it happened? Elastic deformation of the metal. This is the first stage. And second is the piezo viscosity. The viscosity, pressure, viscosity effect. Piezo viscosity, pressure, viscosity effect. So these two effects combine together and creates this, the elastohydrodynamic material. Here you can see elastohydrodynamic, rolling element and area of deformation. Actually, this is the race area. You can see that there's a flat. But when it comes in contact with that, so what happened? The area of deformation, because we have seen earlier very high pressure, gigapascal. So this is the temporary area of deformation, and the lube oil squeezes out from this, the incoming lube oil, and it is outgoing lube oil. So this is something which is the causing deformation in the race area temporarily, and due to this the elastohydrodynamic lubrication exists. Under local contact pressure exceeding hundreds and thousands of the pounds per square inch, the steel surface do not remain rigid. This is the main point. As we have seen, the steel surface do not remain rigid and they deform elastically like a dense rubber. We have seen in the previous diagram, the deformation occurs temporarily and it is acting like a dense rubber, and the lube oil squeezes out between the metal contacts. So that's how the elastohydrodynamic lubrication exists. The narrow line or the point contact squeezes out into a small flat band, and this deformation spreads the mechanical load across the wider area and preventing the contact stresses from destroying the metal. So basically, due to this, it is going to allow the load sharing part also, lubrication part also. So mechanical load is being shared to the wider area, and basically at one point the pressure is not going to destroy the metal. So this is something which is your basic understanding that elastic deformation happens where you have basically the contact line or point, and due to this the temporary deformation takes the load and the lubrication also exists. Okay. And piezo viscosity, pressure viscosity effect. What is this? As the lubricant is dragged in through the microscopic high pressure contact zone by surface motion, the extreme pressure causes the oil's dynamic viscosity to surge exponentially. So dynamic viscosity of the oil changes, and due to the high pressure, it surges exponentially. At contact pressure around 1 to 2 gigapascal, the oil viscosity increases by 10 to the power 4 to 10 to the power 8 times. This is the thing, and this basically takes the load, and your lubrication also happened. So this is due to the pressure and viscosity effect. In short, it is called piezo viscosity effect. The liquid lubricant temporarily transforms into a solid like you have the glass hard protection film. The liquid lubricant temporarily transformed into this. It's a solid like structure, glass like hard protective film while passing through the contact area. This happens only the lube oil passes through the contact area and returning to the liquid form at it exists and pressure will drop. So at that contact point, that line contact or the point contact, this transformation happened in the lube oil, and this is going to take the high pressure and high loads. The pressure around, you can see the 1 to 2 gigapascal pressure at contact points. And the viscosity, dynamic viscosity also changes 10 to the power 4 to 10 to the power 8 times. So you can imagine the situation. And due to this only, the elastohydrodynamic lubrication exists. And as soon as the lube oil goes out, so while passing through the contact area, and once it return to the normal phase or the liquid form, as it exit from that part, and the pressure also drops. So this is something which is a very interesting to understand the piezo viscosity effect in the elastohydrodynamic lubrication. Marine applications, marine reduction gearboxes, rolling element bearing, ball and roller bearings, cam and roller followers. How it is? As the gear teeth mesh along moving line, so what happened? Elastohydrodynamic lubrication keeps the hardened teeth, steel teeth, planks separated and preventing the pitting, micro pitting and scuffing under the heavy torque. So as we have seen the gearboxes, the gear trains are there, the motion happened between them, and then due to the this elastohydrodynamic lubrication is possible. Rolling element, ball and roller bearings. This is found in everywhere, ball and roller bearings, the motors and all, centrifugal pump, fuel oil purifier, turbocharger, rotor and so on. So wherever you find this roller bearings and all, so ball bearing, the contact points, so either the roller contact point or the ball contact point, they have the elastohydrodynamic lubrication. Cam and the roller followers, 2-stroke and 4-stroke marine diesel engine, high pressure contact between the rotating camshaft, lobes and the roller followers, driving the fuel injection pump and the exhaust valve. So we have the elastohydrodynamic lubrication in over there. Okay, we have the cam and we have the roller followers. So there also you will see the curved surfaces and they have the line contact. And so the EHL regime is established over there, elastohydrodynamic lubrication between the cam and rollers. Either we talk about for the, like we have the for fuel injection, the fuel cams and rollers, and or the exhaust valve, we have the exhaust valve, cam and rollers. So there we have the elastohydrodynamic lubrication exists. This is the last part. So thank you. I have tried my level best to make you guys understand the different types of lubrications with the diagram and the better understanding. This video becomes long, but I hope once you go through this video, this is going to make you understand about the lubrication systems, the basically core understanding of the lubrication systems. And I have given you where exactly these are applicable. So this is the most important. So in oral point of view, this is also going to be a good understanding. Okay. Thank you.